So what I'm going to do in this session is to give the properties of this wave function and the property of the Schrodinger's equation, and introduce superposition concept, and finally the application of Schrodinger's equation in quantum mechanics. So the property the wave function must have, the property the wave function must have is, again, the psi should be continuous. The second one is, again, psi function should be differentiable. The third one is, it should be square integrable. I think it's very obvious when we say continuous and differentiable. Let me spend some time on what square integrable means. Square integrable means so again, this is the square of norm of the function, square of norm of the wave function. And if we do that, I mean, if you take the integrable from minus infinity to plus infinity, and it should be less than infinity. So that's what we mean by square integrable. So this is the property the psi function must have. So this is the property of Schrodinger's equation. The first one is, Schrodinger's equation must be linear and homogeneous. The second one is, it's a first order with respect to time, which is equivalent of the second law of motion from Newton in the classical mechanics. So this basically gives the state of a system if you know the state of a system at time equal to 0. So this is the two major properties of the Schrodinger's equation, and let me expand on the first property, what we mean by linear and homogeneous. So let us say psi 1 of r comma t, psi 2 r comma t, psi 3 r comma t, etc. are a solution of this Schrodinger's equation, or the solution, the wave function solution of the Schrodinger's equation. Then the linear and homogeneous means the summation of these, introduce a constant, also a solution. Okay. So here I say R basically is x comma y comma z, so three-dimensional. So this is also a solution. Okay. So let me go to the application of the Schrodinger's equation. Application of Schrodinger's equation. See, let us say in a system, let us say this is a system, assume that it is an n-dimensional system or infinite dimensional system. Let's say it's minus infinity to plus infinity. So this is A and B. So if this is represented by this wave function, again as I said, in the property of the Schrodinger's equation. This wave function is the one describes the state of this system, and we can determine the state of system if you know the state of system at time is equal to 0. So again, I'm talking about the application of Schrodinger's equation. Let us say, what is the probability of finding a particle of the system in space A and B? So to find that probability, so this application of the Schrodinger's equation, or the application of the wave function, I mean, it's again part of the Schrodinger's equation. Gives the probability of finding this particle in that space between A and B. So this is the application of the Schrodinger's equation. Let me write one more time. So the probability of finding the particle between A and B, I mean in the space A and B in the system, is given by this is the major application of the Schrodinger's equation, the wave function. Thank you.